Good morning. Welcome to the PCEA member webinar, PCB Material Properties, Consideration for Design and Manufacturing. My name is Mike Buteau, and I am the president of the PCEA. We have two short polls that we would like attendees to complete. While folks are finishing up completing the polls, let me give you a little bit of background on the PCEA. We are an international network of engineers, designers, fabricators, and anyone involved in printed circuit development. Our mission is to promote printed circuit engineering as a profession by encouraging and facilitating the exchange of information and the integration of new design concepts through education, certification, communications, seminars, and workshops. This is facilitated by a network of local, regional, and virtual PCEA affiliated chapters and the support of our sponsors. For those who don't know, PCEA is a producer of the Certified Printed Circuit Designer Training curriculum. CPCD is a 40-hour course covering the circuit definition and schematic capture, board layout, data and placement, circuit routing and interconnection, materials, manufacturing methods and processes, signal integrity and EMI applications, flex PCBs, documentation and manufacturing preparation, and advanced electronics. CPCD emphasizes real-world engineering and design, not pie-in-the-sky theory. Students are taught facts and principles in a tool-agnostic way. The course, which was developed by Mike Creedon, Rick Hartley, Susie Webb, Steph Chavez, and Gary Ferrari, includes a 400-page handbook, Printed Circuit Engineering Professional, that covers more than 65 major topics, ranging from design to materials and fabrication processes. Registrants may also take an optional certification exam. Learn more at PCEAtraining.net. I'd also like to thank the PCEA corporate members and sponsors, whose logos you see here. Our featured speakers today are Tony Sinise, Group Manager at Panasonic Electric Works, with more than 40 years experience in process engineering and PCB laminates, and Eriko Yamato, OEM Business Development Manager at Panasonic, who has more than 15 years experience in business development and marketing of computer hardware and software, EMC/RF wireless test products, copper foil, laminates, and electronic components. Their talk, PCB Material Properties, Considerations for Design and Manufacturing, will cover key material properties such as T sub G, CTE, and Modulus to guide how they can impact PCB design and processing. The question and answer function is activated and may be accessed in your control panel. Please feel free to submit questions at any time. Questions will be answered at designated times throughout the presentation. Attendees are automatically muted and the speaker cannot see you. The chat function is not active, so you will not be able to communicate with other attendees, just the speaker. At the end of the webinar, you will receive a very short survey. Please help us by completing it. And let me now introduce Eriko Yamato, our first speaker for PCB Materials Properties, Consideration for Design and Manufacturing.
Okay, good morning, everyone. How are you? Let me see. Let me show my screen here. And I think you should be seeing the screen. Thank you again, Mike, for the wonderful introduction. It's great to see the information on PCEA. And myself being involved with the Printed Circuit Engineering Association, it's a great organization. So I encourage you to become, the membership is free and there are a lot of resources. But in any case, yes, today we would like to cover some of the PCB material properties, considerations for design and manufacturing, and also what to look for. And I'm actually going to have Tony open our presentation for us. And I think, Tony, let's see, I think you're unmuted now.
I am.
Okay, so I will go to, I'm the slide sorter for you. Here we are.
I appreciate it. Okay, I'm going to start with a very simple few slides. I think one of the things that most of us that have been in the industry a long time take for granted is the idea that everybody understands that when they're looking at a data sheet, what the possible limitations of that data sheet are. But I'm going to go over a few that maybe you haven't thought of, and then we'll get into the meat of them. So this is one of our data sheets. We didn't want to be commercial, so I'm not going to, there's no identification of what the material is, but it's typical of our data sheets. It has a list of properties, units, test method, condition, and typical values. Next slide. So the first thing I want to explain is that data sheets are not all inclusive. Data sheets are only a snapshot of the product line. Some of the test methods are similar from vendor to vendor and some are not the same. Next slide. These property values are only true for the specific sample that's tested. So if you look at the bottom where the arrow is, you can see that in this particular case, most of these samples were a 30 mil core. Now, I think if you knew which product this was, you would understand why that's not representative of everything that you use. And most of the materials we sell are much, much thinner than that and much higher resin content. And that means that the values represented for those tests where that node applies are typical values. They're values that you can use to compare to other products in a general way. But if you put those values into a finite element model or any sort of simulation, they're not going to represent what you see in the real world. Next slide. One of the other things that I think people misunderstand is that a lot of times the value of one of these data points is influenced by the test method. And as you can see, the two test methods that we call out on this data sheet for glass transition temperature actually are quite a bit different. And I could talk for hours about why, but if you don't know which of those test methods has been used and somebody says, well, the TG is X, whatever X is, 200, 150, 1, you have to know the test method. And if you don't know the test method and you try to compare to another product with a different test method, you will not make a good comparison. Next slide. Now, the other thing is that not all properties for the same parameters are measured under the same conditions, not only between different suppliers, but often between different products from the same supplier. In this slide, you see that the dielectric constant is reported at 2 different frequencies. If I showed you 5 of our other products, that 1 gigahertz number is probably always reported because it's a typical IPC value with an IPC test method. But the 13 gigahertz number is not typical. Some people might report 10 gigahertz. Some people might report 16 gigahertz, depending on their test method. In this case, Panasonic uses a balanced type circular disc resonance method. That is not a standard required test in the industry. It's what we chose at the time this product was developed because it gave us the best information at the frequency that most of the customers were interested in. And as I think most of you know, is that changes from generation to generation of material. And I think that's my last slide.
No, actually, you had one more over here.
Oh, I have one more?
Yes.
Oh, that's right. You should always look when you're looking in a set of data from a supplier to see if there's any Easter eggs. One of the Easter eggs in our data sets that is not always published on the web, but is often part of the package that we hand out at a trade show or is online as additional data, is that we've measured and verified at different frequencies for both DK and DF for a lot of our products, because it helps you to understand. If you look at the resin content column, typical resin content, you can see that there are from 56 up to 70% represented in these constructions that are all for different thickness laminates. And you can see that for DK, there's certainly an important difference between them, and it's different for frequencies. And we started doing this with this generation of product about 15 years ago, and we've continued, but we don't publish it usually on the web because we figure that by the time a customer gets to this point, we have a relationship with them, and it's probably not going to be a competitor that's downloading this information, or probably would be a competitor that downloads this information. And that is my last slide, Erica.
Thank you, Tony. And I forgot to mention at the top, we'd like it to be more interactive webinar. So feel free to ask questions during the chat. And Mike, for the purpose of me not getting distracted, I've actually minimized that section. So if any questions come up that might benefit the group, feel free to share that, interrupt me. So it's not a one-way street and a two-way street. But yes, one of the reasons I really wanted to do is this because in my daily job, I stare at a product property chart a lot. In my past job, I did a lot because I was in charge of making the marketing collateral and having the correct values on the data sheet. But that was it. I was focused on the data sheet. But now these days, obviously, I talk to customers and they're looking for certain characteristics. And today I wanted to pick a few of these properties that come up a lot and are key deciding factors for different applications when you're looking for a material. And I wanted to start with, okay, TG. Tony had mentioned earlier the different methods of measuring the glass transition temperature. And I'm sure many of you know that glass transition temperature is when a material transitions from like hard, glassy state to rubbery, more flexible state. And actually, so I mean, we did show you the snapshot, but I wanted to bring this again because in the other one, it only had 2 methods. But here, I have 3 different methods, and as you could see, these values are different. And I've actually made the mistake of someone mentioning about the TG, and they were talking about TMA, but I was talking about DMA, and some materials have a lot bigger gap. So the first method is the TMA, and that is the thermal mechanical analysis, which measures the dimensional changes in the material over temperature. And this can include expansion or contraction of the material. And just wanted to also add TMA method is used for CTE, which I will cover later in the presentation. Now, for each test method, I have listed commonly referenced standards, such as the IPC and the ASTM, but I'm not going to go over these, especially with the IPC. You could download these test methods, so you could study at your own time if you'd like. I mean, one of these standards could take us like a whole webinar to cover the test method. And you could also look at the ASTM standards, I think, which you would have to actually pay to download. Okay, and the second method is the DMA, the dynamic mechanical analysis, which measures the elasticity of the material over temperature. And as I had mentioned earlier, due to the nature of the test methods, how they're measured, the values are different. And typically, if you look at it, the TG by DMA is higher than TMA. And you can see in the example property here, see the TMA value is 165 degrees, whereas the DMA is 190. And finally, the DSC is a method that measures the changes in the amount of heat required for a sample to maintain a static heat rise rate. And this is an indirect test method. Any questions so far on the method? Can't see. All right, and I'm going to move on to, so how does TG, what should you consider when you're looking at a TG on a property chart? Okay, so typically higher TG materials have a lower expansion and higher modulus, whereas the lower TG materials have better adhesion. These are just the characteristics. But in any case, if you, depending on the application, you do have to find the right material with the right thermal characteristics. For instance, these are just reference numbers, so it's not exactly the range of TG. But for instance, for commercial applications such as phones and tablets, TG of 130 degrees to 150 should be appropriate. But for applications that require or are exposed to high temperatures, like telecom applications, servers, or automotive electronics, you should look at materials that have higher TG over 170 degrees or so. So what about things to think about for manufacturing? Higher TG materials have a better dimensional stability, and dimensional stability is very important because any changes in the dimensions of the PCB could lead to variations in the electrical properties that could potentially affect the performance and reliability of the circuit. And those of us in the PCB industry understand the importance of reliability of a board. And additionally, with higher TG materials, it requires higher temperature for processing, and the PCB ends up being more brittle. What does that mean? So since the board is more rigid, it will be a little bit more difficult to drill. Finally, higher TG materials tend to be thermally and mechanically more robust. What I also wanted to do here is show you an example of what a characteristic the data looks like with a TMA method. And Tony, if you'd like to add some comment to what we're looking at here today with this example.
So this is a typical scan of what would be kind of FR4 material, very common material. This was done in a test that was done in a consortium that we're a member of as a function of about 500 different tests to evaluate and quantize the ability of TMA to measure TG accurately. What you see in this scan is that the curve has a deflection point, and you can see right there it's around 160 C. It's hard because of the way the tangent lines have been drawn across it to see the whole line, but basically the rate of expansion below that TG and the rate of expansion above that TG are critical parameters. And the measurement of that is very accurate, at least for each sample, because the way the machine works, it has a small stage with a highly calibrated, very precise monitoring of the Z-axis position of a quartz probe. That probe sits on the sample, and then as you heat up the chamber in a controlled way, it measures the position. And there's a bunch of other steps in the procedure to make sure that works well. But you get a very accurate measurement of the Z-axis expansion over temperature. It's often plotted over time as opposed to temperature, because the rate is set at a specific rate. Like in this case, it was 10 degrees C. You can see up at the top, it says CTE 10 degrees C. That's the IPC test method rate, and it's fairly accurate for most materials. But one of the problems that has been discovered is that this curve is not always such a hockey stick. Often it is a more smooth curve. So drawing the tangent lines and picking the tangent lines is very critical. The expansion is very easy to measure no matter what the curve looks like. It could be a straight line or it could be a round curve, but if you pick a temperature, you can get an almost exact measurement of the expansion of the sample. But to know what the TG is, it's a little bit more difficult on some materials. And if you have questions about that or you want to know more about that, we can talk about that some other time. That's a whole different conversation. But what it means is TMA is a good way to measure expansion and not such a good way to get a precise TG. So if somebody asked me, how do you measure the TG? I would say the most accurate way to measure the TG for a lot of the new materials is by DMA. There you go.
Fantastic. Any questions so far on TG?
Erica,
Yes.
Erica, yes, there are a few.
Okay.
Why is the 0% change point shown at the knee rather than at 25 degrees Celsius? It
is one of the anomalies of this test. And in order to explain it, I would have to show you the entire thermal history of the sample. But suffice it to say that the zero position is set when you put the sample on the stage. A scan is done to relieve any stresses or remove moisture that's from the sample preparation. The sample is often prepared using a diamond saw with a wet process. And so the first scan is to settle the probe on the sample as part of the IPC procedure. And often the position of the zero moves down. And that's, so if I could show this to anybody that wants to see what it actually looks like over the series, but it's very common for the zero to go below the 0 point that the probe sat at when you put the sample in the chamber.
Next question. Is expansion in X and Y axis relevant and measured or only in the X axis? Sorry, or measure, sorry, let me rephrase. Is expansion in X and Y axis relevant and measured or only the Z axis?
So yeah, that is relevant. It's a good question because X and Y axis expansion, and I don't know if we have a detailed slide about this, but
we do. Yeah, I'll cover CTE. Yeah, I'll cover the expansion.
XY CTE is a figure of merit on the, and is measured. It is sometimes measured by TMA. It can be measured by TMA. It is also measured by other methods using a different setup so that you can get a more accurate XY. The Z-axis expansion is important for a lot of reasons, which Erica will cover. The XY expansion is important for other reasons and is a much lower number in the 10 to 15 parts per million range for most materials, and is highly affected by the construction of the sample because the glass has a very low expansion and the resin has much higher expansion.
Another question. Can you explain how to understand higher T sub G means PCB is more, quote, brittle, but also mechanically stronger?
Without going into a whole bunch of things about how you formulate the product, I can't explain it in detail, but what I can say is this. All thermoset materials, and that's what we're talking about here, have a cross-link density. That is basically the length of the average size of the polymer in the cured state. Higher TG materials usually have a higher cross-link density. The reason that matters is that as the length of the chains of the polymer get shorter, the flexibility of the plastic part of our material goes down. So the way I think about it is if you have a rubber band, it's very flexible, but not very strong. And if you have a piece of steel, it's very strong, but not very flexible, at least over the range of forces that we use. And those two are way extreme. They're way outside of what we make. But in that plastic range, the glass dominates in the XY and the resin dominates in the Z. And the resins at higher TG have evolved over the last 30 years to include fillers, which also make it more rigid and hard, not brittle. So they have to be optimized. And the lower TG materials, like probably the one that's described on this slide, flex better, flex more, and are a little more, because of that, because the polymer chains are longer, have better adhesion.
That's it for the, yeah, that's it for the questions in the queue for now.
Great. Thank you so much. All righty. So now we've talked about TG, the glass transition temperature. I also wanted to include the decomposition temperature. Now, of course, as the word decomposition implies, this is the temperature where material decomposes chemically. Now, and a decomposition process is often irreversible, as opposed to what we're looking at like a TG, the glass transition temperature. But once it reaches it and cools off, normally the material will go back to its original state. And have included an example of material with a TD, but some product chart may or may not have this decomposition temperature. But the method used here is the TGA method. What I also wanted to do was, because, well, I used to confuse myself with the TG and the TD. I wanted to kind of do a comparison and see what kind of impact, similar impact does it have on the design/manufacturing, and what differences they have. So a couple of similarities. If the material has higher TG and higher TD, the material will have higher resistance to delamination during multiple reflow cycles. And also these materials will survive better in extreme temperature environments such as automotive applications. So better for use in extreme temperatures. This also means that higher TD materials are going to have better resistance to multiple lamination cycles. And few things that are specific to higher TG materials. You'll have a reduced Z-axis expansion. We talked about expansion, and plated through-hole stress. And higher TG materials can also endure longer desmear time. However, as mentioned in the earlier slide, higher TG material will cause more, well, because it's more brittle, more drill wear. And I understand that drills are very expensive. So that is relevant for those in PCB manufacturing. Okay, so another thermal characteristic I would like to touch on, which we kind of talked about in that earlier slide, is the CTE, the coefficient of thermal expansion. So CTE shows how material change with a change in temperature. And specifically, it measures the fractional change in size per degree change in temperature at a constant pressure. Higher the TG, the more the material will expand in reaction to being heated. And we talked about earlier the XYZ. So CTE is measured in both XY and Z axis directions. And with glass reinforced material, the CTE and XY axis is not as high as the Z axis, as the glass cloth provides strength and limits the expansion. Now, as the material temperature, the material heats up, it follows a linear expansion rate until it achieves the glass transition temperature. And as we saw earlier, for once it reaches that TG higher than TG, the material expands at a different rate. And looking at this example here, so it has the XY and the Z axes, and you can see there's alpha 1 and alpha 2. So the difference between the alpha 2 and alpha 2 values are alpha 1 is below TG and alpha 2 is above TG. And as we kind of talked about earlier, you could see right here. So let's look at just the Z-axis here. So Z-axis for this given material, alpha 1 is 45 parts per million, as opposed to CT and alpha 2 is 260. So significantly higher than alpha 1. Okay, next slide here. What are some of the things that you want to consider for design? And I'm sure those of you who are on this webinar that have designed PCBs come across this topic a lot, CT mismatch, and I hear that a lot too. So you really want to avoid CT mismatch to eliminate mechanical failures. Rule of thumb is to select materials with similar CT values in the same stack up. Don't use materials that have a lot of different CT values. And this goes the same as well for components that are being assembled on the board. Make sure they have similar CT values. Some other things to consider are component placement Place them symmetrically on the PCB to distribute thermal stress evenly. Of course, I mean, this may be difficult in some design where you have space constraints. And better distribution of copper will also help. Thought it might be helpful just to have examples of what the CTE is for some materials like standard FR4, PTFE, and copper here. And so we talked about CTE mismatch. What is the impact of having CTE mismatch? And I'm a very visual person, so I wanted to add this image here. I think you can see here, it's a cross section of a material, and you can see actually the board is warped and there's delamination. And what happens when you have mismatch? You can also, especially with the boards that have a higher aspect ratio, copper coating along the via walls tend to be thinner, making the center more vulnerable to thermal stress and cause cracking. And another thing to think about is chip package. I know today we're talking more about PCBs, but the chip package usually has a lower CTE, a lot lower than the PCB. So when the board is heated, the package will expand less than the board and can result in a bad solder joint connection. Obviously, the difference in CTE will matter more when the chip package sizes are larger. Tony, did you want to add a little bit to this? And since you actually found this cross-section image for me, some examples, stories about what other problems can occur with CTE mismatch?
Well, there are a lot of things that relate to CTE mismatch. You described a few of them. We could be here months talking about it. But this particular picture is from a test that was done to differentiate materials that were made with two different types of material. And you might be able to see in the picture the 4 layers of copper. And this is a simple 4-layer structure that was designed to evaluate resistance to delamination in a hybrid structure. So the prepreg on the outside of that inner layer core is different material than the prepreg used to make the inner layer core. And this was a test that was done to evaluate, I think we had about 10 different combinations. This was done within outside of Panasonic in a group that we participate in. And our goal is to make a test method that can evaluate these different combinations to see if they work, so that you don't have to build boards before you know that there's a mismatch that might cause delamination. And this test is kind of in the early stages of development, but it is critical because a lot of the newer designs use more than one material. And the industry has a lot of work to do, especially when we start doing a lot of build-up constructions. That's it.
Great. Any questions on this section for CTE?
Glad you asked. Is CTE ever measured with a high density of through holes or stacked microvias, or is it always on laminate blanks? I have heard that there is a rivet effect to dense Z-axis structures.
So the answer to the first question is it's often been tried to measure using a method like TMA, the differences in different areas of circuit board, depending on the copper loading, depending on the plated through hole loading. And it's not a very good way to do it because the probe is about 5 millimeters. Some of the probes are actually up to about 10 millimeters, and you just can't put the features are too close together to measure the difference. But the other thing that's been done in some consortiums beyond the modeling and trying to verify the model is actually one of the things that's been done is called digital speckle. I'm going to get this wrong. Digital speckle imagery. A professor at a Canadian college developed this method so that you could take, for instance, this cross section that's on the screen and put small particles on the surface. I don't really know the process that he uses. He won't tell anybody. And then take images of the expansion over temperature at a very, very high resolution using an algorithm and a special photographic monitor. Looking at each pixel, he can see the movement of those speckles over the temperature. And then you get an idea of what the stress is, in where the stress risers are in the model. And that's been done, and there's a lot of information developed by a few consortia about especially structures that are where you have micro vias, blind vias, buried vias, stacked and staggered, to see the difference. We don't really look at the overall expansion when we look at those things. We're really looking at the very, very micro, because that's where the failures happen. That's where the fatigue happens, and to try to figure out what causes that in the design. So there's a lot of information about that, and anybody who's interested, I'd be glad to talk about it more.
Yes, this is a very deep topic. Any other questions, Mike?
We do have a couple of people who have asked whether slides will be available after the presentation.
Yes, the slides will be available, yes. All right. So now we've talked about a few thermal properties. Let's move on to mechanical properties. Modulus. All right, and typically when people are talking about modulus, they are referenced the Young's modulus, and that was my assumption too, but I've had cases where engineers were referencing other types of modulus, so I just wanted to list it here just to differentiate. Young's modulus, also known as the elastic modulus, is a measure of the stiffness of material. So it quantifies how much a material deforms, elongates, or compresses under a given amount of force. And the flexural modulus, or the bending modulus, is a material property that characterizes the stiffness of a material under bending or flexural deformation. It is a measure of a material's ability to resist deformation under applied bending stresses. And finally, the shear modulus, which I don't think you hear as much, is a property that measures the stiffness of a material under shear deformation. And when I first started learning about modulus, I was very confused. Well, these are all modulus, so how do they measure it? And I'm a very visual person. So of course, where do I go? I went to the internet and I looked it up, and and there are really cool videos out there once you start looking at modulus, how these properties are measured. But I really like the Young's modulus. It's very, very clear. Just you put a weight on here and you see how that wire it expands with that added force. And then like the flexural modulus, you could see where they put the force on to measure that modulus. But again, this is a pretty deep conversation that if we get into the test method, it'll take one webinar to cover at once. So I'm not going to go into the detail, but let's look at what the effects would be for design and manufacturing for modulus. But for me, again, I really like this example here, the Young's modulus example. So let's say my favorite stone, diamond. It's a 1220 gigapascal compared to like rubber. That's like 0.01 gigapascal. So higher the modulus, stiffer the material. All right, so when you're looking at a design, you have to think about the overall stiffness or what kind of flexibility your application requires. What is the overall thickness of your board? So if, for example, if you're working on a dynamic flex application where your board is flexing a lot, right, repeatedly, you would want to look for a lower modulus material. And similar to what I had mentioned in the CTE section, select materials that have similar modulus values to avoid mechanical issues. And any questions on the modulus?
Nothing so far.
Nothing so far? Okay, let's move on to the Next mechanical property characteristic is the dielectric strength. I wanted to list a few, and I think typically when people talk about dielectric strength, we do reference the breakdown voltage, which you'll see in a lot of materials property charts. It's pretty much the breakdown voltage is the threshold at which the initiation of material breakdown occurs. And there's also the high pot test. And what's a high pot test? High potential test. It's a dielectric withstand test that verifies that the insulation can withstand higher than normal voltages without breaking down. Now, this test is more often used to test a thinner dielectric material, obviously, to look at the insulation, like embedded capacitance material that are under 2 mil thickness. That's because it's more critical. And it's a pass or a fail test depending on the voltage, and that voltage requirement will differ based on the application. If you're looking at a commercial application, it might be 250, but if you're looking at things like telecom applications that go through a more intense environment, they'll be tested at 500 volts. Another way to look at dielectric strength is the CAF, the conductive anodic filament test. The material is monitored when voltage is applied to see if there's growth of conductive anodic filament. And these three, again, I mean, there's a lot more depth into each of these tests, but I won't have time to cover it. But what I did want to mention, I would like to mention a few things to consider when looking at the dielectric strength of the material, just to make sure to choose material that meets the application voltage requirement, because if the laminate cannot handle the expected voltage of an application and break down prematurely, the device can malfunction. And for higher voltage designs, such as telecom applications that consume a lot of power, consider materials that have higher dielectric strength. And a couple of things on maybe CAF here. If CAF occurs, that can cause short circuits, and CAF formation can be accelerated when exposed to high humidity and elevated temperature. Any questions on the dielectric strength?
What is the best way to specify the PCB material on the fab drawing notes? Slash sheets, OEM material? I know this is it depends on type of question.
That's a whole new seminar.
Yeah.
I'll tell you what the practice is, and you're going to be surprised. Because I was chairman of the 4101 committee for a long time, and we spent a lot of time on the specification sheets to try to help people come up with generic grades that will meet their requirements. And the truth is, any standards body can't move fast enough to keep up with the changes, and IPC is no exception. So we never really were able to stay out in front of that. Once we started, I don't know if everybody understands, but FR4 is still half the material used in the world. But 10 years ago, FR4 was 75% of the material used in the world. And that means all that growth came in materials that really weren't very well specified out in the industry, but could be used and needed to be used for a lot of reasons. So what people started to do is qualify materials specific to their design and require that material to be used until somebody else qualified. The most common way for materials that are not standard, high-end materials, is for a specific material to be called out, and then new materials qualified and added as they become out in the industry and useful. But I would say that never stops any OEM from specifying a different value for a different application. CAF testing, for instance, it's the Wild West. It goes everywhere from 5 volts to 5,000 volts, depending on the application. And temperature and humidity can be from really benign room temperature and humidity all the way up to 85% humidity at 85 or higher temperature, and any combination of all those three things. And the reason that exists is because the density requirements in the circuit board affect CAF. The thickness of the circuit board affects CAF. The hole size affects CAF. And the fabricator's cleanliness affects CAF. So it's a pretty complicated thing to try to cover in a standard specification. And even though we tried to give some hints in the IPC specification sheets, they weren't very useful because every application required something different. High-pot testing, like Erico said, is really important when the dielectrics get very thin, because once you go down to a single ply of fabric in a dielectric, one defect can cause failure. So the cleanliness of the laminator's process is really important. But the percentage of the material used out there in the industry that has to pass a high-pot test is very small. Breakdown voltage, usually they're so much higher than what's required. It's not a critical variable to specify unless you are using very high voltages above typical household current. I hope that doesn't confuse you too much. That's the answer.
It's not a one answer type of question, variables. Okay. And we have just less than 10 minutes. I wanted to just go over the last mechanical property, which is the peel strength, because this does come up a lot when speaking with customers. And there are two types of probably peel strength that you'll hear about. One is the peel strength of the copper foil. So when we're talking about CCL. And I wish I actually had included a drawing because, but I didn't have time to do it. But I hope my verbiage, this explanation helps. But the peel strength for the CCL is, like I said, the peel strength of the copper foil bonded to the dielectric. The peel strength of buildup layers. I mean, it's pretty much the same thing, but it's a matter of where you're looking, which copper that you're looking at. So when the buildup layers, you're looking at the peel strength of copper foil bonded to the prepreg. Maybe actually when I distribute the slides, I'll include an image so it's crystal clear. But this is an example of peel strength here for a material, and this is for the CCL. This is one of our products. I forgot which one I pulled it off of, but this is the one for the peel strength of CCL. And a few things to consider.
Just so you know, CCL is, and I hate to be like this, but I just want to make sure everybody understands copper clad laminate.
Oh,
it's
yes.
It's something all of us that make laminate use but it doesn't occur in the wild.
So what I'll do is, like I said, I'll actually add an image to the slide, because I think then people will be like, aha, okay, that's what she was talking about. So I will do that. All right, and lastly, so you know, I know a lot of engineers reference, and I've personally interfaced with customers that are looking, hey, Erico, I'm using this material crossing, blah, and they just compare all the properties, right, to make sure they're comparable. But when you are looking at the peel strength, the IPC standards, the standard calls to test with the 1 ounce copper. But a lot of times, especially with all the ultra thin coppers out there, like microthin, that are like less than 3 micron, the test results are going to be different. So just look at the values, and it could be lower because it's not apple to apple comparison. Something to think about. And Tony, do you want to add to some things to consider for manufacturing?
Sure. So the thing about copper adhesion, and this is the part that I think a lot of people don't really understand, that peel strength value of 0.7 kilonewtons per meter it's a prorated, which basically means if the line width goes down, it's a function of the total adhesion of that circuit. That means the thinner circuits are not adhered to the surface as well and are more prone to damage. The finer the lines are, the easier it is to damage them. The buildup layers are not tested for peel strength by the supplier of the material, because that material is generally not used as is, and you can only test it once you've made it into a structure. I think it's interesting that most people don't understand that microvia layers that use, say, an MSAP process to define them, the peel strength can't be measured. The last thing is, in the history of circuit boards, the last bastion of hope for fine lines and spaces is often solder mask, solder resist, because once you coat a circuit, it's very hard to damage. So those are things that you should keep in mind. If you design a circuit that's going to be on the outside of a board, and it's very fine, say 50 to 100 microns, and you don't put solder resist on the surface, it's very easy to damage. That's it.
All right, we only have a few more minutes left, but are there any questions?
What's the best way to know decay values at specific frequencies pre and post fabrication?
That's a really good question, and it really depends a lot on what the fabrication is. If you do one lamination, the data that we showed at the beginning is pretty much what you need to know. If you do multiple laminations, and there are people up in the 5 to 10 laminations, the value can shift depending on the material, and every single material is different. You need to talk to the supplier about the thermal history that you're going to put your board through to figure out how it changes. We publish data when we know somebody is going to use a material and there is drift of the value over temperature because of a number of factors.
All right.
Any others?
There was a question about how many pounds per inch in a kilonewton /m.
0.7 kilonewtons per meter is 4 pounds per inch. So just there is a easy calculator or easy way to calculate it. I don't have it on my desktop, or I would show you. But if somebody wants to contact me later, I can send that information to them. It's a direct calculation engineering value.
And then we have a question, what about a new IPC design standard for PCB materials for designers based on design requirements? For example, signal rise time, application temperature, and then the person adds, I know that's a lot to ask.
First thing I would say is, and I'm not an advocate of IPC. IPC doesn't pay me for anything. But I would say that in the meetings that I've been in that are design standards related, there are anywhere from 2 people, which is usually a chair and the co-chair, up to 200. And because of that, there are a lot of competing priorities about that have to do with specific different designs between suppliers. So developing a design standard is a long process, but it is always in motion. There are several design standards that IPC is working on, and I would say the best way to help make that happen is to participate. IPC meeting is in April of this year in Anaheim, and I would encourage anybody that wants to find out more to attend that meeting. The standards meetings are basically free. So participation will show you the process that we're trying to go through for those design standards. IPC is one of the biggest organizations in the world for these kind of things, which is good and bad because it means there's a lot of stakeholders with competing priorities. But you could see the process, see what how the sausage is made in those meetings. And it's not always pretty, but it does yield useful standards eventually.
I agree. I have been involved with the 4101 committee, and it's been a great experience, not just looking at the, just the literature itself, but I think if you've never been to a standards committee meeting, like Tony said, it is free. And I think not just attending, but I think actively being involved if you would like to be, well, because obviously, I mean, the standards are standards, but it has to serve the community, the PCB community. So definitely encourage you to be a part of it. But since we have hit that 11 o'clock time, I would like to thank you all for taking your time, your busy time of the day to join us. And if you do have any questions, we will, this is our contact information here, Tony and myself, and the slides, after I add that cross-section image, I will send that out to Mike, so it'll be distributed. But in closing, I would like to add that, yes, today we covered insights of how to look at a property chart and help you select the right material. But that being said, these are for your reference in designing the board, but ultimately you will not know for sure until you build the board and run the reliability tests. Tony, any closing comments?
No, I think you covered it very well. Thank you, everyone.
All right, thank you so much.
Thank you for joining us for PCB Material Properties, Consideration for Design and Manufacturing. You will receive a link to the on-demand recording shortly. This webinar has been sponsored by the PCEA Certified Printed Circuit Designer Training Curriculum. Learn more at pceatraining.net. And of course, thank you to our presenters, Tony Sinise and Eriko Yamato. If you have any questions, please contact the speakers, or you may contact me at mike@pcea.net. Have a great day.